Bienvenidos y bienvenidas a las sesiones y a las conferencias de la Fundación Ramón Areces. Hoy tenemos con nosotros al profesor Christopher Jones, Chris Jones. And Professor Jones is a professor of the Chemical and Biomolecular Engineering at Georgia Tech. The School of Chemical and Biomolecular Engineering at Georgia Tech is ranked the second undergraduate program and the fifth graduate program in chemical engineering in the United States. And Professor Jones is part until responsible can claim responsibilities for this success. Because indeed, he has been vice president for research for a long period of time, and not only first associate, but then also executive vice president for research. Professor Jones leads a group that works on materials, catalysis, and absorption. And he's very known by his pioneering work on materials that extract CO2 from ultra-dilute mixtures, such as ambient air. Well, this you will see later in the talk, that is a key issue. At the end, we can extract hydrogen from water, but then we need carbon for our life and for functioning in this world. And the carbon, the source of carbon, if we forget about fossil sources, the places where we can find it is from biomolecules and from the CO2 present in the air. So this is a very timely and very exciting research that Professor Jones is doing. In fact, it's so much so that he served on the National Academy's consensus study on negative emissions technologies and reliable sequestration. And there they were focusing on the direct air capture. So they have informed what can be the technologies and how to reach the final objective of extracting the CO2 from air. Professor Jones is also responsible because he was the founding editor-in-chief of the most successful today journal in Catálisis, which is the American Chemical Society Catálisis. The success was so big that right away the American Chemical Society provoked him to make a new journal, JAX AU, that we call in the media JAX Gold. And this is now again being a great success. The work of Professor Jones on CO2 separation and sequestration has been recognized by different awards. I just will say that they are awards from the American Chemical Society, North American Catalysis Society, AICHE, and practically all the organizations devoted into that. Today, he will be giving us a talk, and the name he gave was Development and Deployment of Negative Emission Technologies, Humanity's Moonshot for the 21st Century. Well, in his lecture, he will describe not only the materials that he has developed and he's developing to capture CO2 from such a diluted streams, but also how those can be done to be able to make realistic projects, realistic production at the end. And you will see that this can only be due by combining the materials that will absorb and will desorb, but not only that, but also the engineering the unit operations, and by combining all those, it is possible to reach now numbers that start to look reasonable, and to see that that possibility of capturing CO2 from the air is possible. It's not just a dream. Chris, thanks very much for staying today with us. I really appreciate that you accepted to give us that talk, and please go ahead.
Hello, everyone. My name is Christopher Jones, and I'm a professor and school chair in chemical and biomolecular engineering at the Georgia Institute of Technology. I'm going to talk about development and deployment of negative emissions technologies, which I'll refer to as NETs. And I think of this as society's grand challenge today, targeting mitigation of climate change. And I'm happy to have the opportunity to share with you some of our research in this area. I'll begin just by telling you a little bit about myself and where I work. So I am in Atlanta, Georgia, in the southeastern United States. It's the most significant city in the southeastern quarter of the United States, so it's a big business hub. We have the world's busiest airport, so very easy for you to come and visit us. I'm at the Georgia Institute of Technology, which is one of the largest colleges of engineering in the United States. And we have a very strong program in chemical and biomolecular engineering, of which I am a part. And a particular aspect of our program in chemical and biomolecular engineering is that we have a very strong cadre of researchers studying gas separations. And this has been leveraged then to work on CO2 removal from different sources, such as flue gas, as well as from the ambient air. So I'll begin with my key messages, and then I'll finish with my key messages. The first key message is that as scientists and engineers, quite often while we are solving problems, we create new ones. And I think you can trace back the current climate problem back to about 1900, when scientists and engineers were working on the other grand challenge of that time. And that grand challenge was famine. So if we were to look at major newspapers around the world in about 1900, the topic of significant discussion would be the number of people dying due to famine and the lack of food. So if we look in Wikipedia, we can see that many times in the late 1800s, there were many millions of people dying in different parts of the world. So scientists and engineers, as well as policymakers, came together and focused on a solution. And one solution that's very famous now is the Haber-Bosch process that was able to fix nitrogen or convert nitrogen from the air into precursors for fertilizer. And prior to that time, most fertilizer came from nitrate minerals mined in Chile in South America. And after Haber-Bosch developed this new technology to produce a larger amount of fixed nitrogen, the cost of fertilizer dropped by more than half. And of course, now that we are able to feed humanity, this led to a massive population boom in the 20th century. So if we look at the historical record, we can see that it took about 250 years prior to Haber-Bosch for the population to triple. But then after Haber-Bosch and the ability to feed people more efficiently, in less than 100 years, we had a 4 times increase in population. So it's really this population boom that has led to very significant energy use, which has led to significant CO2 emissions, and therefore the grand challenge of the current time, which is climate change. So that's my first take-home message, is that we've created this problem as scientists and engineers with the Haber-Bosch solution to famine. This problem is now climate change that we have to mobilize and work on today. The good news is that history shows that science can respond in a rapid and focused way when it's properly resourced. And examples coming from the United States perspective include the Manhattan Project in the 40s, the moonshot in the 60s, and then the Human Genome Initiative in the 90s. So given that climate change is a defining challenge of our current era, this era being 2020 to 2040, I think we need to focus significant attention on this, because history will look back on this period and reflect on what contributions we as scientists, business leaders, or policymakers contribute. So one solution to climate change is a class of technologies called negative emissions technologies. These, when coupled with renewable energy, will provide the answer. But there's no single technology that by itself can solve the problem for us. So what we need is a variety of scalable negative emissions technologies. And I believe that we will continue to use fossil feeds like gas and oil to make chemicals and materials for a very long time. And that nets are going to provide us a means to extract CO2 from the atmosphere, most probably for sequestration underground. One sort of net that I am involved in is called direct air capture. This is removing CO2 from the air, and it's an area where expertise in chemistry and chemical engineering, my fields of sorbent molecules and materials, coupled with chemical processes, can allow us to bring significant impact. So if we look at emissions mitigation and CO2 removal, we're familiar with ways to reduce our carbon footprint, to reduce carbon sources by focusing on energy efficiency or low or zero carbon fuels. If we were to do carbon capture from a point source, like a coal or gas-fired power plant, that would also produce a way to reduce carbon sources. To look at point source CO2 capture, this is represented by this image from the IPCC report in 2005. And for point source CO2 capture, such as cement or steel plants or electricity generation plants, we want to develop technologies that can capture that CO2, provide a concentrated CO2 stream, and then we can use that for profitable uses, making chemicals, or we can store them permanently, sequester it, if you will, geologically in the ocean or in minerals. So this point source capture is practiced today. I'm going to refer to that as traditional CCS of CO2 capture with storage. And we need a wider implementation to slow the pace of worsening of climate change. However, point source capture, as well as these other renewable energy technologies, only produce a product that we refer to as avoided emissions. It simply slows the rate at which we are making the problem worse. We need to couple these products on the left with new products in the center, where we are enhancing carbon sinks. And these are referred to as negative emissions technologies, and they produce the product referred to as negative emissions. Recently, I was part of a study in the United States conducted by the National Academies of Sciences, Engineering, and Medicine, where we looked at all of the ways that you could remove CO2 from the atmosphere using land-based methods, so not ocean-based methods. And these include bioenergy with carbon capture and sequestration, changing the way we manage the land, such as forests and farms and coastlines. My focal area was on direct air capture, removing CO2 from the air, which when coupled with geologic sequestration gives you a negative emission technology. So if we think about these negative emissions technologies, what is the potential market likely to be for these? Or equivalently, how much carbon uptake is needed to meet the Paris Agreement goals? So we can consider that by looking at this plot, which is a plot of greenhouse gas emissions as a function of time. The business as usual path is shown in yellow, and you can see if we follow the business as usual path, we will maximize emissions mid-century, and we will get much more than 2 degrees C warming. Climate experts believe we should try to keep warming below 2 degrees C, and to achieve that, we need to follow a line that looks something like the red line. And to achieve this red line, noting that we're about right here at the apex of the line today in 2022, we need to start rapidly reducing emissions, and we need to create a new type of technology, those negative emissions technologies, represented by the blue in the diagram. So you can see that these start to come online in a significant way around 2030. By about 2050, we should hit 10 gigatons of CO2 removed per year. And by the end of the century, we want to hit 20 gigatons of CO2 removed per year. So this is a very huge and rapid increase in technology development. And it's essentially creating a new technology, 25% of the 2020 fossil fuel industry in 30 to 40 years, or 50% the size of the fossil fuel industry in the next 75 years. So this is a huge challenge, and it requires rapid and smart technology development. So let's think about the history of removing CO2 from the air. This is something that as a society, we've known how to do for a long time. And of course, we can all think about technologies developed for spacecraft or submarines, where we have to remove CO2 from confined spaces in order to allow people to live and work. So we've been doing that throughout the 20th century. But it wasn't until 1999 when Klaus Lackner, then working at a national laboratory in the United States, he's currently at Arizona State University, proposed large-scale direct air capture as a climate change mitigation methodology, where you would suck CO2 out of the air, concentrate it, and store it underground, for example. Of course, you could also use this to make value-added products. So it took about 10 years for the first temperature vacuum swing absorption direct air capture companies to form. And about that time, I began working closely with one of the companies, Global Thermostat, where we combined sorbent technology from Georgia Tech with process technology from Global Thermostat. So at that time, we visited the US Department of Energy and advocated for government funding to support research in this area. But unfortunately, at that time, this topic was not viewed to be potentially scalable. There was a previous report that was done in 2011 by the American Physical Society that says the technology was going to be very, very costly. And that analysis was correct. The technology is costly, but at that time, it was not yet recognized that the costs could potentially be reduced significantly with significant R&D. So we spent the next 5 to 7 years doing significant R&D. And then in 2018, the Negative Emissions National Academy study was published that I referred to earlier that suggested that lower costs were in fact possible. There's been great growth in this field. So in 2016, we wrote the first comprehensive review of direct air capture, shown here on the right. It had about 250 references. And now 6 years later, authors in China wrote the follow-up review. There's now 550 reports studying direct air capture. And I note that approximately 20% of those come from researchers from my institute or alumni from my institute. So my institute plays a very heavy role researching this topic. So in this report that I referred to, there were two principal authors of the direct air capture section, myself at Georgia Tech, and then Jennifer Wilcox. And we're very lucky in the United States to have Jen now as the Principal Deputy Assistant Secretary for the Office of Fossil Energy and Carbon Management. She's also a professor of chemical engineering at the University of Pennsylvania, and she's really championing negative emissions technologies in federal government policy. And what this means now is that we have substantial funding now for R&D in this space in the United States. It took about 10 years from our first advocacy to the Department of Energy in 2010, and it was really catalyzed by that National Academies report. And in the last several years, we've had many billions of dollars of research as well as development and deployment funding available from the Department of Energy. So at Georgia Tech, we have a very strong focus in this space. We've recently launched the Georgia Tech Direct Air Capture Center, which we've named after the famous physicist Paul Dirac. So Dirac, as we call the center, brings together scientists, engineers, and public policy experts. Collectively, even though it's a relatively young field, we've published more than 150 papers on direct air capture. And we're going to have a center kickoff meeting this November in Atlanta. So if you or anyone else is potentially interested in attending, you can reach out to me. We already have 10 corporate partners who are going to attend and participate in the discussion. So we named this center after Paul Dirac because he's one of the first scientists who discussed the particular challenge of dilute mixture separations, which is of special importance to CO2 removal from air. And he worked to identify the minimum work or power required to achieve that sort of separation. So at Georgia Tech, we've produced many graduates who are now significant leaders in negative emissions technology, several of which I show you on this slide. And in particular, for folks in Spain or as well as Latin America, I would direct you towards Dr. Micaela Taborda-Claur, who works at Repsol. She's a former PhD student of mine. She's a world expert in direct air capture, started her career working at ExxonMobil, and now is working in Madrid. Originally from Bolivia, she would be a great resource for anyone in Spain who's interested in direct air capture. So my expertise specifically in direct air capture is designing the agent that can selectively trap the CO2 in the air while not trapping other components in the air like nitrogen or oxygen. We can imagine these CO2 adsorbents are existing in many different types. And I describe them here as a function of their capacity for absorbing CO2 in moles per kilogram as a function of temperature in degrees Kelvin. And the challenge that we're trying to deal with is a very dilute mixture. So a very, very small amount of CO2, much more water, and even more oxygen and nitrogen in the air. So we need to have a sorbent that gives good selectivity to CO2, and also a sorbent that we can scale up and deploy commercially. So a lot of chemisorbents are very good from a selectivity perspective. They form chemical bonds with CO2, and they can give you very high absorption capacities. Unfortunately, they tend to operate at very high temperatures. If we want to do CO2 capture near ambient conditions outdoors, we need to work at low temperatures. And at low temperatures, we mostly have physisorbents that have weak discrimination between CO2, water, and other molecules, and therefore they aren't as good from a selectivity perspective. We identified a class of materials that are low temperature chemisorbents, so offering the selectivity of these high temperature materials with the low temperature operability of these physisorbents. And these are we're going to refer to as organic, inorganic hybrids. And in particular, we use a lot of amine modified materials for this purpose. So when we started working in this space, I and my collaborators outlined 5 key needs that are required for a practical process that removes CO2 from the air. First is a low pressure drop, high surface area contactor. Second is an adsorbent with good thermodynamics, so good binding of CO2. And I'm going to spend a little bit of time doing a deep dive into the science of designing these types of sorbents. We also need an adsorbent that can cycle quickly, adsorb and desorb CO2 very quickly. A sorbent that allows for low cost adsorbent regeneration, because this is where we have to put significant energy and money into the process. And then we need a process and materials with low capital costs and materials with a long lifetime. So we'll begin with item number 1, a low pressure drop, high surface area contactor. This is important because we have to move a lot of air through the process compared to a point source, which is much more concentrated. As a figure of merit, to remove 1 ton of CO2, if we're moving 70% of the CO2 that passes through the device, we need to process 3,500 tons of air. So low pressure drop is very important, and we can achieve that with things like monolith contactors, which are already commercially available from a wide variety of vendors. And many of you who have petrol car powered or diesel powered cars own these in the catalytic converter of your car. So rather than coating them with catalyst, we're going to coat them with sorbent materials. And doing so in a low pressure drop contactor is important because if you don't, the fraction of the overall cost for moving air can be up to 1/3 of the total process costs. We want to have this cost be as low as possible. So monoliths are not the only form of structured contactors. At Georgia Tech, we've worked on a wide variety of other types of structured contactors, with many of these projects being led by my colleague, Professor Ryan Lively. So we can also have structured contactors with low pressure drop based on sheets or laminates, 3D printed type structures, such as this monolith here, as well as either hollow or solid fibers. And so all of these form factors are under investigation at Georgia Tech within the Durox Center. So examples of publications that we have produced recently using these different types of contactors. So these are the devices that are going to be used to display the amine materials that I talked about earlier that are going to selectively grab the CO2, where we can put them in a cylindrical aluminum monolith, where the walls of the monolith are coated with porous alumina, which are then coated with a polymer like polyethylene imine. We could also make those solid fibers. These fibers are made of cellulose acetate, so the type of polymer that's used in your frames for your glasses or in cigarette filters, but then loaded with amine sites that can capture CO2 selectively. Or most recently, we've used laminates based on fluorinated polymers like EPTFE, again, incorporating mesoporous solids containing amines that can capture the CO2. So there's many types of structured contactors that could potentially work in this application. So the area that I've spent most of my time studying is the binding site for CO2. And I focus my attention on low temperature chemisorbents. So these would be porous oxide materials functionalized with basic groups such as this primary amine shown here. And these chemisorbents that form chemical bonds with CO2 offer steep adsorption isotherms, where we have the amount adsorbed in moles per kilogram is a function of concentration or pressure of the species, in this case in bars. So we can see we have a steep isotherm when we have a chemisorbent that then levels out at higher pressures. In contrast, for a physisorbent, we have a relatively shallow isotherm that then gets much larger at higher pressures. So physisorbents don't give you the uptake that you want at low pressures, and so we focus our attention on chemisorbents. In parallel, my colleague Ryan Lively, who I mentioned earlier, along with Matthew Ralph, published a paper studying the thermodynamics of separations as a function of the level of dilution of the feed. So if we were using a CO2 natural gas deposit that is 50% CO2, you could get a good thermodynamic separation efficiency using pressure swing adsorption. But if we go to something like ultra-dilute systems such as air, these curves all go down to very, very low separation efficiencies. So the conventional separations, pressure swing adsorption, are not very useful for these dilute feeds such as air. Fortunately, temperature swing adsorption, where you adsorb at low temperature and desorb at high temperature, does work well for ultra-dilute systems. So if we go to 400 parts per million, moving to the left from 1, we can find that we might expect an ideal sorbent for ultra-dilute separations to have a heat absorption on the order of -55 to -65 kilojoules per mole. This is well within the range of chemisorbents and very close to the values I showed you on the previous slide for the amine materials that we use. And TSA is good for ultra-dilute separations because you're putting the primary energy in after adsorption on the concentrated product, where here we put the primary energy in before adsorption on the dilute mixture. So given that we want to have chemisorbents, we want to have them in a porous substrate, I'm going to show you one detailed study of what we've done to understand the role of the binding site, in this case, the amine that binds CO2. So when we work with the startup companies and our corporate partners, we typically will take a polyamine, incorporate it into a porous support, and we'll often use a polyethylene imine as our model solid. This is very a scalable approach to make large volumes of sorbent. But to do precision science, it's sometimes better to have only a single type of amine site. So here we're going to graft a single type of amine site onto a similar porous host and study how it binds CO2 at the molecular level. So we did that by creating a porous host, a silica host, with a surface area of 200 meters squared per gram, a common pore volume, and a common amine loading. But we're going to vary the structure of the amine such that the sorbent has all tertiary amines, or all secondary amines, or all primary amines. And we can then measure isotherms in moles per kilogram as a function of pressure. And we can measure them at multiple temperatures. And the black data are for primary amines. The blue data are for secondary amines. And you see there's no data for tertiary amines because under dry conditions, they don't bind CO2 via chemisorption. So we can see from this that the primary amines are the most favorable for absorbing CO2 at very, very low pressures found in air. And secondary amines are also potentially useful, though not as useful as primary amines. So the classical way an adsorption scientist would analyze this is we would fit these curves with an isotherm, and then we'd apply the Clausius-Clapeyron equation to back out a heat of adsorption. And from this analysis, we would surmise that the primary amines are more effective than the secondary amines because they have a higher heat of adsorption or a higher binding energy, stronger binding with the CO2. So our take-home messages early when we started working on this 10 years ago was that primary amines offer the highest uptake, and that's a type of amine that we should target in our sorbent development. Well, we decided to test that hypothesis that primary amines are better than secondary amines because they offer higher heats of absorption. So we did that by using a calorimeter, in particular a customized Ceterom Calvé calorimeter, whereby we can dose in trace amounts of CO2 and very accurately measure the heat evolved in a batch system. And so this allows us to measure the sorption isotherm and the heat of adsorption simultaneously with great fidelity. So we can do that, and we're going to do that on a family of materials now that only have those primary amines that I showed you were the most useful. And we're going to change the loading of the primary amines on the surface. So all the binding sites are the same. We're only changing the density of these binding sites. And what's interesting, when we go from bare silica to a low loading of amines to a high loading of amines, we see a nonlinear response of the CO2 uptake with the amine loading. And so only when you get to very high amine densities do you see a very significant CO2 uptake. And we can rationalize this by doing in situ infrared spectroscopy and identifying the structure of the CO2 as it forms on the surface of the amines. And what we see at low amine loadings is we're primarily forming carbamic acids. And these carbamic acids don't have a strong driving force for binding. They don't have a significant heat absorption. And as a result, we get moderate uptakes. But as we increase the density of the amines, eventually we get a second amine close to that carbamic acid. And now we can form an alkylammonium carbamate with two amines binding one CO2. And this gives us a massive jump in uptake because these cooperative N-CO2 N intermolecular interactions are strongly enthalpically favored. So we have a very significant heat absorption associated with this chemical reaction. And again, we can identify these structures using in situ infrared spectroscopy. So if we now compare those sorbents with the heats absorption that are measured experimentally, we can see that the high amine loadings give you high heats absorption, absolute values of the heats of absorption. So strongly negative, minus 90 kilojoules per mole. And bare silica is a physisorbent, so it doesn't give you very significant uptake. And that's owing to the mechanism of absorption shown here. We can now circle back and look at different amine structures. So what I just showed you on the previous slide was for one amine, the primary amine, the aminopropyl site. But previously I showed you when we studied the aminopropyl and the methylaminopropyl, or primary and secondary amines, that the primary amine was more efficient in red than the secondary amine shown in blue, as I showed you earlier. And we hypothesized that was due to differences in the heat absorption. Well, now we can measure the heat absorption for all of these different amines, again at the same amine loading on the same type of silica support. And if we begin by looking at the primary and secondary alkylamines, we can see that they offer different uptakes, though they're all effective, with a primary amine being the most affected at low partial pressures. But we can see that they all have the same heat of absorption. This is not what we concluded in our previous study. Previous study concluded that the primary amine was more effective because it had a stronger heat absorption. These data here, however, show that's in fact false. And what that means is that if the primary amine is not better due to enthalpic reasons, it must be better due to entropic reasons. And the entropic penalty that we think is associated with the second arm on the amine. So when this is a primary amine, this is a small hydrogen, which makes it easy for this carbamic acid to find another amine to form that alkylammonium carbamate. But now if you put a steric hindrance in here in the form of a second alkyl chain, like a methyl or an N-butyl, you have to get this second chain out of the way on both sides in order to form this alkylammonium carbamate. And these entropic penalties associated with moving those chains around, we think leads to reduced CO2 uptake. We can further increase the steric constraints by going to something like a cyclohexyl group. So this is similar electronically to the N-butyl group. So it should be the same basicity of this amine site. So in principle, it should bind CO2. But now the secondary amine is so big, we can't form any alkylammonium carbamates. We see almost no uptake beyond the bare silica. So steric constraints can be very important to designing good CO2 binding sites in these materials. So knowing now that we want primary amines, and we want them to be very sterically non-congested, with my collaborators, I've worked for the last 10 years to design next generation amine polymers for CO2 removal. So what can we use after we've deployed polyethylene imine? Are there any materials that could offer potential advantages? So we've put an aromatic ring in the center of a PEI or PPI type structure. We've made polypropylene amine or PPI type structures, as well as made side chain based polymers that are rich in primary amines, such as polyallylamine, as well as polyglycitylamine. So that gives you a little bit of insight into designing specific sorbent materials that can selectively pick out CO2 from a dilute mixture. I now want to talk about the other three elements more briefly: adsorbents with good kinetics, adsorbents that can be regenerated with low cost, and then processes that have low capital costs and long sorbent lifetimes. So we'd like to cycle this adsorbent between adsorbing CO2 and desorbing CO2 as quickly as possible. That would allow us to minimize the amount of sorbent we need. And to remind you, to remove 1 ton of CO2 at 70% removal, we have to process 3,500 tons of air. So we want to do this as quickly as possible. We look at the normalized capacity, where 1 is equilibrium, as measured in a thermogravimetric analyzer as a function of time. We can see that getting to equilibrium can take a very long time, even up to a day on these types of sorbents. But we're not going to run these sorbents to equilibrium. Instead, what we're going to do is we're going to stop when we exit the linear regime of adsorption and then desorb at this point. So rather than going 700 minutes to get to equilibrium, we can go only 100 minutes, get 80% of equilibrium capacity, and then desorb and collect. Now in a TGA with non-ideal flow patterns in the laboratory, that takes about 100 minutes. But if we take that same sorbent and now put it on a monolith contactor, we can increase the gas velocity to much higher values while still having low pressure drop. We like to run at about 5 meters per second. And that takes that 100-minute value to get to 80% capacity and reduces it down to about 15 minutes. So low pressure drop contactor does 2 important things for you. 1, it gives you that low pressure drop, so that means low fan costs for moving air, but it also gives you the ability to cycle quickly by reaching this pseudo equilibrium at 80% of equilibrium capacity in only 15 or 20 minutes. So the 4th challenge, after we've loaded the CO2 onto the surface of the sorbent, is we need to get the CO2 back off and collect it as a pure species. With pure CO2, we can then upgrade it into value-added products for society, chemicals, fuels, etc. Or we could potentially store it underground in order to combat climate change. And I'm focused on storing it underground. So we want a low-cost source of energy. And the nice thing about these amines is they capture at low temperatures, and we only need to use a small delta T for regeneration because the heat of adsorption is not too high. So we can go to 40 to 80 degrees C to desorb. And on our adsorbent that's collected CO2, one way to desorb that we favor at Georgia Tech is to put steam through the sorbent itself. The saturated steam can condense on the sorbent surface. That liberates the CO2, and then we get a mixture of steam and water that's relatively easy to separate, giving us pure CO2. This approach requires a very robust adsorbent because direct steaming is somewhat harsh, and you have to keep that in mind when you're designing your sorbent material. Another approach we favor at Georgia Tech is joule heating. So this is where we might take a carbon fiber, coat it with a sorbent layer, as Ryan Lively's group has done recently, and then apply electricity through the carbon fiber, and then use the resistance of the carbon fiber to heat the fiber quickly, say from ambient conditions to about 100 degrees C, which can be done in a matter of seconds, and then cooling back down again. And you can see that when we do multiple adsorptions in a breakthrough here, whereby we're adsorbing CO2, which would normally be at a value of 1, it gets adsorbed at about 360 minutes, it breaks through and goes back to the starting concentration. So we've adsorbed and saturated the sorbent twice. If we do a conventional temperature swing adsorption, we get a more diffuse pulse of CO2 out, so we're going to get a lower purity and yield here. Whereas we do this electric swing adsorption, we get a very sharp peak associated with this joule heating. So these are our 2 preferred modes of desorption for these amine sorbents. And then the 5th element that we need for a practical process are acceptable capital costs and our ultra-long process and material lifetime. And particularly for amine adsorbents, sorbent degradation and lifetime is a critical element. So I've been working with a startup company, Global Thermostat, which is incorporating sorbents designed in my group under license from Georgia Tech with their commercial scale air capture process. The first unit that they developed as a demonstration unit was in 2011, 2012 in Menlo Park, California. It did about 1,000 tons per year. And then in 2018-19, generation 3, I have pictures of that as well. These are shipping container sized modules through which fans blow air. Fans go in through the walls and out the top. And inside the walls here is where the sorbent is contained. Global Thermostat originally developed their R&D labs at my institute in Atlanta, Georgia, and recently in 2020 moved to their independent facility in Brighton, Colorado. So I received research funding from this company, as well as I have a financial interest in the company. So I have to disclose this conflict of interest statement here when we talk about this topic. So let's look at a hypothetical techno-economic analysis of a TVSA process similar to what, but not exactly like the global thermostat process. So here, rather than using the global thermostat sorbents, we're using a MOF film containing amines. on a monolithic contactor, and we're going to model Mil 101 chromium loaded with PEI 800 molecular weight. We'll fit those isotherms experimentally, and then simulate a process that involves an adsorption step, an evacuation step where we remove the air from the sorbent, steam pressurization and desorption, and then cooling back down to room temperature, at which point we can start absorbing air again. And this overall process, as well as the materials involved, are described in a series of papers, including the original powder sorbent, putting the sorbent onto a monolith, and then designing the process and the technoeconomics. When we use a 40-minute cycle time, we calculate an energy of separation of about 0.15 megajoules per mole CO2. This is larger than the minimum energy that you would calculate from thermodynamics, which is good. That means it's that's a sanity check and tells you that you've got a reasonable number. And if we compare this to post-combustion capture at a point source with a much more concentrated feed, it's only slightly more energetically expensive for direct air capture compared to post-combustion solvent capture. And this is the piece early in the development of direct air capture that was not obvious to many people, is that even though we have a 400 times more dilute feed, say coal-fired flue gas compared to air, we only require between 1 and 3 times more energy for operating the separation. So this gives us potential scalability. And most of the startup companies I'm familiar with are imagining a scale-out approach to scaling this. So mass manufacture of small shipping container-sized units that would capture CO2 for concentration and sequestration. So if we think about these now 5 key elements in a practical process that removes CO2 from the air, we have a low pressure drop contactor, check, I showed you that. We need an adsorbent with strong binding energies with good thermodynamics, check, I showed you the amines do that very well. We need to be able to cycle it quickly. Well, we can do that on a monolith contactor as well. So we've demonstrated that on the lab scale. We can do low cost regeneration at relatively low temperatures by using either steam stripping or joule heating or other approaches, to be honest. We've done that on the lab scale. And then for acceptable capital costs and ultra long process material lifetime, we've demonstrated that as well on the lab scale. So there's a couple areas where I think there's a lot of room for improvement. I think current costs for CO2 capture from air quoted from the startup companies are in the range of $400 to $600 per ton. And we really need to get that cost down to $200, hopefully by the end of this decade, and then down to $100 by a decade further. Because if we can get it to $100 per ton, then we can imagine massively scaling globally this type of technology. Most recently, we've added a 6th element that we have started to work on in the last few years, and this is technological flexibility. And what's really unique about direct air capture compared to most chemical processes is you have a very significantly changing feed. Not necessarily from a CO2 concentration perspective, that will change depending on how close you are to a road or a city, or if you're more in a rural area. But because of changing during temperatures and humidities during the day, as weather patterns change, as you go from day to night, and especially seasonally as you go from summer to winter. So in deployment, we're going to need to have real-time sensing of the CO2 partial pressure, the temperature, the relative humidity, and other factors, so that we can change the cycle in real time on a daily basis to have it be optimal. And we discussed that in a recent review paper we just published this year in the Korean Journal of Chemical Engineering. Unlike typical chemical processes, for example, if you had a catalytic cracker in Spain, in Kuwait, in Brazil, or in Texas, it might operate essentially at the same temperature, pressure, conditions in all of those locations. That's not going to be the same case for direct air capture, where we have to operate maybe in temperatures ranging from -30 to 50 degrees C, and with humidities ranging from nearly zero all the way up to full saturation at high temperatures. And one of the things we noticed in the literature is that what I'm going to call subambient temperatures have not been well studied. Mostly room temperature indoors and higher have been studied. And this makes sense because we're doing these experiments indoors in a laboratory. But we think cold temperatures offer many advantages: favorable thermodynamics, weaker CO2 binding, as well as less competition from water. So for example, we think you might even be able to use a physisorbent if you work at very cold temperatures. So if we look at the concentration of water in air as a function of temperature, At ambient conditions, there's about 30,000 ppms of water at the dew point at 100% relative humidity in the air. This water, which also adsorbs on physisorbents like zeolites, makes it essentially impossible to use zeolites at these high temperatures because you have to expend so much energy drying the air before you can use the zeolite. In contrast, if you go to cold temperatures, say -20 in Alberta, Canada, or Alaska, or Norway, or Finland, you can imagine that the the water concentration being much lower now does not compete as much with CO2, and maybe you can use zeolites or physisorbents. And in a recent paper we published in IECR, we did a simple energy analysis, and we think that at cold temperatures, you might be able to first dry the air and not incur too large a cost, and therefore be able to capture CO2 with a relatively low total energy of about 4.4 gigajoules per ton of CO2. While physisorbents might work at cold temperatures, we need to evaluate all sorbents at cold temperatures. And if we look at the globe on the left and the US temperature regions on the right, we can see that the majority of the data in the literature are at ambient temperatures, which I'll call 20 degrees C and higher. And that only covers a relatively small part of the world for average temperatures. In contrast, the majority of the land on Earth has average temperatures below 20 degrees C. And you can see in most regions in the United States, most regions are below the 20 degrees C throughout the year. And so we need to do more work as scientists and engineers studying direct air capture at what I'll call subambient temperatures, so below 20 degrees C. So I'll show you our first study under these cold conditions. We're going to again use that PEI impregnated MIL 101 chromium MOF. So this is a porous metal organic framework containing a polyamine that we previously studied in 2016 at 25 degrees C, showing good CO2 uptakes of about 1.2 moles of CO2 per kilogram of sorbent. And our aim was to see what happens if we now take this sorbent that seems to work well at 25 degrees C and now operate it at cold temperatures, say winter in northern Canada. So we studied the adsorption as a function of two amine loadings, PEI, as well as tetraethylene pentaamine, which is a shorter chain version of PEI. We loaded it at 30 weight% in the pores and 50 weight% in the pores. And at ambient conditions, 25 degrees C, we can see that there's a nonlinear response to amine loading, just like I showed you earlier. Denser array of amines gives higher uptakes at these higher amine loadings. In this case, up to about 2 moles per kilogram for the sorbents using TIPA. However, when we now go to -20 degrees C, we see these high amine loading materials have a significant drop in performance. Reduced CO2 adsorption at these conditions, we think because of significant pore blocking, the CO2 can't get into the pores at these cold temperatures in these densely filled pores. In contrast, at medium loadings, we see enhanced adsorption at cold temperatures. This is likely due to a thermodynamic effect where adsorption is favored at cold temperatures and there's still enough space in the pores that we can get CO2 in efficiently. So what's the take-home message from this simple little plot? And that is that we're going to need different sorbents that will be optimal for different climates and different seasons. So if we were going to use this family of sorbents in a cold climate, we would want to use the 30 weight% material in the winter. And then maybe in the summer in northern Canada, where it can be 10 or 20 degrees C, we might want to use higher loading amine materials. So we're going to have to adopt the process and the material to the location and the climate. So as I finish, I'm going to answer two questions that I commonly get before they're offered by anybody in the audience. And that is this really practical from a land area perspective? So I'll do a calculation for you. Let's imagine we are going to do the entire globe's need of negative emissions by DAC. That would be 10 gigatons per year. I hope we will never do this because this would be the most expensive way to do negative emissions. We need to bring the cost down for DAC still. But let's imagine we did it. If we had to do the entire globe's needs for negative emissions. According to the startup companies that I've talked with, the estimated land area required to do 10 gigatons is about 150,000 square kilometers. So in the US, that's roughly the size of my home state of Georgia. So while we would not do this in one location, in a populous location such as Georgia, the point is that this amount of land somewhere on Earth, maybe distributed over 100 different locations, is certainly tractable. So we are not going to be limited by space on land in order to do the amount of negative emissions that we need if we have to go to even this crazy high number. The second common question I get is, why don't we just use natural systems like trees? And of course we should. We should use natural processes as much as possible first. Those are typically lower cost, and they're obviously more compatible with the environment, making less environmental harm. However, as a society, as a species, human beings are still mostly deforesting. We're not doing a good job of reforesting, especially if we look in Latin America or the Southern Hemisphere in Asia. There's still a lot of deforesting that's going on. But from a technological perspective, these DAC processes are actually even more efficient than a tree at the equator. So if one goes into the scientific literature and calculates how much CO2 a tropical tree at the equator will use, and then normalize that on the ground based on the ground area, we would calculate a flux of 20 micromoles per second per meter squared of ground area that a tree removes CO2 from air at that flux. The DAC process designed by human beings is about 25 times higher. So if we want to normalize by ground footprint, we're more efficient than a tree at the equator. Nonetheless, I still favor natural solutions first if we can do that. I don't think we're doing it quickly enough, which is why I think we need to deploy DAC as soon as possible. So if I cycle back to my key messages about removing CO2 from the air, scientists and engineers solve problems. We're going to solve the climate change problem too, I hope. Sometimes when we do it, we create new ones. And in fact, scientists, in my view, created the climate change problem by producing enough food and energy in order to enable a population boom. We can do this based on history. We're going to be judged as a generation of human beings about how effectively we are a steward of the globe based on how well we address this problem. And I think direct air capture is going to be one component to the solution. Georgia Tech has got a lot of people working in this space, and we're poised to help other researchers around the world work in this space as well. So as I finish, I'd like to acknowledge and thank my collaborators. Anybody who's written in bold has data that I used today in the talk, so they contributed in some way to the talk, including former and current students, former and current postdocs, and then also senior collaborators have also contributed as well, shown here on the left. I'll thank my group, and I'll thank those who fund my research, including many parts of the Department of Energy, the National Science Foundation, ARPA-E, as well as some companies, some of which have chosen to remain anonymous, some of which are happy to share their name. If anybody's interested in motivating younger people to go into careers in STEM, I think climate change and direct air capture is a nice tool that can show the importance and the impact. And recently, the Dreyfus Foundation did a 7-minute video on direct air capture of CO2. It's very accessible to 10 to 18-year-old students, and hopefully we'll direct them to STEM careers. If you're interested in that, you can find it at this URL. So with that, I'm happy to stop here. I don't know if we'll have questions immediately. If not, if anybody has questions they would like to share with me via email, I'm happy to answer those at the appropriate time. Thank you very much.